So here we have this stroke option. This is Cambridge style, whereas in the United States we would have Vmax is in the units, parentheses in the units, millimoles over seconds. The Cambridge style is Vmax stroke millimoles seconds to the negative first power. So that is the same thing. When you are writing your exam, you need to pick one and stick to it. My suggestion, just write whatever Cambridge already used and said. All right? If they already gave you in the exam a table with units, use that unit. All right? So here are just some samples of Michaelis-Menten constants in millimoles and Vmaxes in millimoles per second. So 8,000 millimoles carbonic anhydrase is the Km, 600,000 millimoles per second. This is not something you need to memorize, so we're just going to move forward. So despite all the evidence to the contrary in the previous few slides, this is not a math class. So let's take it back to the real heart of the matter. Enzyme affinity, which I'm abbreviating as EA despite for the fact that EA is enzyme activation energy. So please don't get confused. This is not like an accepted abbreviation. I'm just doing this for my own edification, for my own ease of use. But enzyme affinity. How readily the enzyme-substrate complex is going to form. So Km and enzyme affinity. A low Km means that you will have a high enzyme affinity. A substrate concentration will be, you will need a low substrate concentration required to reach your Vmax. A high Km will be the opposite. High Km means low enzyme affinity, and you will need a lot of substrate before you reach Vmax. So, an enzyme with a low Km, blah, blah, blah. Easy saturation will also make this enzyme reaction less susceptible to changes in substrate concentration. So, remember your enzyme substrate, remember your substrate concentration curve here, that there is a point of saturation. If you have a low Km, that means that after you've reached your saturation point, you can do whatever you want to the concentration of substrate. You're not going to affect your rate of reaction. You can do anything you want after you've reached your saturation. You can add, you can subtract. Past that point, you are basically just going to have fun with it. So we can extend this to determine the response of an enzyme's rate of reaction to changes in substrate concentration if it has a high Michaelis-Menten constant. So these are our graph differences. So a high a low Km versus a high Km. This Km is below 20. This Km is above 20. So I've continued drawing this past this point. It would probably like reach Vmax somewhere over here. Now, this one will have our high enzyme affinity, low Km, high affinity. We'll take less substrate concentration to reach Vmax. We are there by 60, whereas here we have to go past the graph in order to reach our Vmax. These are our Km differences. But the Vmax is unchanged. Now, here they are on the same graph. Low Km, high Km, same Vmax. So, now that we have grasped what enzyme kinetic graphs in math, I want you to remember this. Concentration of inhibitors and regulatory molecules. Remembering the first four factors that affect an enzyme were temperature, pH, concentration of enzymes, and concentration of substrate. So, types of inhibitors. Let's talk about the types of inhibitors. We have reversible and irreversible. Reversible inhibitors will bind non-covalently and can be removed from our enzyme. We have competitive inhibitors. Competitive inhibitors, by definition, compete with the substrate for the active site of the enzyme. They will share an active site with the substrate. Non-competitive inhibitors reduce the efficiency of the enzyme without affecting enzyme-substrate binding. So, oftentimes it's hard to separate non-competitive from allosteric, but we're going to try for one very specific reason. It's a difference in our Michaelis-Menten equation difference. It changes our graph. So, our non-competitive inhibitors are going to bind to the enzyme, or bind to the enzyme substrate, or bind to the enzyme, or bind to the enzyme substrate complex, or something along those lines, and they're going to prevent the enzyme substrate complex from moving to product. But they are not going to prevent the enzyme and the substrate from coming together at all. So the substrate can still bind to the enzyme, uninhibited, but product cannot form. That's a non-competitive inhibitor. Product cannot form. Substrate can still bind, product cannot form. Allosteric effects. These are often equated with non-competitive inhibitors, but they're on their own classification for the purposes of Cambridge. You can activate allosterically as well as inhibit. We will have a table on that one as well. So an allosteric effect is where you will bind somewhere else besides the active site. An allosteric effector will bind somewhere that is not the active site. So if this is my active site, my allosteric site will be here. And it will change the shape of my enzyme, either allowing the enzyme to bind to substrate or not allowing the enzyme to bind to substrate. There's also uncompetitive, where the enzyme substrate complex is bound to by the inhibitor specifically, but you won't be tested on it. Irreversible. Reversible can be found in all of these types, so can irreversible. The only difference is that irreversible will have a covalent bond form. So it will be mostly permanent effects. It is not the same as denaturing the enzyme. It is covalently bonding to the enzyme and preventing its use in the future. Now, here is competitive versus non-competitive. This is the chemical equation. Enzyme plus substrate gives you enzyme-substrate complex. This is a reversible reaction. The substrate can be pulled off. The enzyme, and this gives you enzyme and product. That is irreversible. You can also have enzyme plus inhibitor, and that will give you enzyme inhibitor complex. That cannot move forward to a product. But this is also reversible. You can get your enzyme and your inhibitor back. So, enzyme and inhibitor, they have the same shape here and here. They can both fit into the active site. They can both fit into the active site, but one can continue to product and the other cannot. Non-competitive inhibitors. Enzyme and inhibitor can form an enzyme inhibitor complex. Enzyme and substrate can form an enzyme substrate complex. Enzyme substrate complex can form enzyme and product. That's fine. But enzyme substrate plus inhibitor can get you enzyme substrate inhibitor complex. Enzyme hyphen substrate hyphen inhibitors complex. Enzyme inhibitor plus substrate can get you enzymes hyphen substrate hyphen inhibitor complex. So here we have our active site, and we have another site right here. So the substrate can bind, and we get our enzyme substrate complex. Here, we can get our product form out here. If inhibitor binds, it can bind somewhere else. If inhibitor binds, it binds somewhere else and prevents product formation. Substrate can still bind to an inhibitor, enzyme inhibitor complex. It is not competing. It is not preventing substrate from binding. It's fine. But it's not going to form product if the inhibitor is there. Now, how is this going to affect our enzyme kinetics? Km reflects enzyme affinity. So an inhibitor that allows binding as normal, but prevents the actual enzyme function, will only lower Vmax, but Km will be maintained. However, an inhibitor that will prevent a substrate from binding to the active site, effectively lowering enzyme affinity, will raise Km. But Vmax is not affected by Km. The value of Vmax is not tied to Km. So, with enough substrate concentration, Vmax can still be reached. So this is why we make a distinction between non-competitive and allosteric. Allosteric is going to affect the shape of our enzyme, which affects enzyme affinity. And it does not, and it also prevents product from forming. So it will affect our Vmax and our Km. Non-competitive will prevent a substrate from forming, it will prevent a product from forming, but it will not prevent the enzyme substrate complex from forming. So Km will remain the same in a non-competitive inhibitor, but Vmax will be lowered. So in a non-competitive inhibitor, Vmax will go down, Km will remain the same. In a competitive inhibitor, Vmax will remain the same, but Km will lower. No, rise. Right the first time. Km will rise, therefore lowering enzyme affinity. In an allosteric inhibitor, you change the shape of the enzyme, the shape of the active site, you affect enzyme binding, therefore enzyme affinity, and you decrease product formation, decrease Vmax. So Vmax and Km will both change. So, this is what it looks like. We have a normal enzyme, uninhibited. A competitive inhibitor will have the same Vmax, but a different Km. A non-competitive inhibitor will have the same Km. If we follow this line, 1/2 Vmax is still the same as 1/2 Vmax. A non-competitive inhibitor will have the same Km, but a different Vmax. An allosteric inhibitor will be a different curve altogether. It will be a different normal enzyme. It'll just be a different enzyme altogether. So it would be, for example, that. Just a different curve. That would be an allosteric inhibitor. Now, allosteric effectors. We have allosteric inhibition and allosteric activation. This is very simple. This is not a complex topic. We have inhibition here. We have here our inhibitor, an allosteric site. We have an active site, a substrate that could fit into this active site if it were allowed to, and our enzyme right here. If this inhibitor binds to this allosteric site, it will change the shape of the active site and the substrate cannot bind. Allosteric activation. We have an active site that is not able to bind this substrate. An activator binds to the allosteric site and it activates the enzyme, allowing the substrate to bind to the active site. That's it. That's all it is. Irreversible inhibition. The process is very similar to reversible inhibition until you reach the dead end complex, EI asterisk, EI, uh-oh. So these can be extraordinarily useful to us commercially, like for example in pesticides, but you really need to be careful with these because, well, they'll kill you. So there's that. Enzyme substrate can still form our enzyme substrate complex and give us our enzyme and our product. But if you add your inhibitor, if it is a competitive inhibitor, an irreversible competitive inhibitor, then we will form our enzyme inhibitor complex. And then if we don't get to it in time, we can form a covalent bond, and then we get our dead end complex. This can be reversed if gotten to fast enough. If it is a non-competitive inhibitor, or a uncompetitive inhibitor of some sort, or an allosteric of some sort, then we can have our enzyme substrate complex that our inhibitor binds to, and that can form our enzyme inhibitor complex that forms our dead end complex. Our K inactivation right here, our kinetic energy of inactivation. So that is enzymes in a nutshell. Let's talk about enzyme immobilization, the last topic in Unit 1. An immobilized enzyme. Immobilized is unable to move or stationary. An immobilized enzyme is an enzyme that is physically attached to a solid support over which a substrate is passed to be converted into product. Now, why bother doing this? So, a single batch of enzymes can be used multiple times rather than mixing one into the other and then having to separate it again and do a lot of chemical processes to deal with that. That's annoying. It's worthless. Also, we can just stop a reaction at any time. We can just we can remove the enzyme card or pour off our excess reaction, whatever we want. Fish out the bead. If you immobilize an enzyme, it'll typically be more stable at the end of that process. Our final product will not be contaminated with enzyme, so we won't have to remove the enzyme from our final product. In food or medicine, in medical or food applications, this is particularly useful. We have a stamp that tells us the half-life. This increases the duration of our enzyme's lifespan. We also have predictable decay rates. We also don't have to deal with preparing our reagents, so it's cheaper in terms of production. Now, this is an example of the different graphs that give us more stability. We have a higher temperature range of recovery rate of product given the same enzyme. So this is free tannase. Our optimal temperature is lower, and we have a narrower range of temperatures we can work over compared to immobilized tannase, where we have a greater range and a higher temperature. If I can work commercially at higher temperatures, that means I don't have to spend money to cool my machinery. That saves me money, that makes me happy as a business owner. Now, in terms of pH, if I have higher activity at different pH ranges, even if my enzyme denatures past these points, that means that I can work over a broader range of solubilities and compounds and solvents, and I can do a lot more stuff with that. That makes me happy as a business owner. So, immobilization methods. Films and coatings. Enzymes are on a layer or a thin piece of material. This is best used for biosensors, where we're using an enzyme to detect the presence of a substrate or in a solution by reacting with an enzyme. Selective adsorbents. So enzymes are immobilized to a matrix, and fluids that contain the substrate to be reacted is then passed through the matrix. It can either be left in place or removed by a second chemical process. It is useful for filtration, which becomes commercially useful for food, waste management, and medicine. And then we have controlled release. In controlled release, you have a gel, and that gel dissolves, and eventually you will release these particles of your enzyme as you go. So this is somewhat how scratch and sniff works, also how the enzyme beads in laundry detergents work. So as the temperature changes during your wash cycle, those beads will dissolve in the water of your wash cycle, and then the enzymes will be able to work. All right? So this is very useful for pharmaceuticals and commercial detergents. So here's two starter examples. We have alginate beads. Alginate is just a gel made from algae. So we have immobilized lactase. lactase is an enzyme that converts lactose to galactose. Okay, once the camera stops wiggling, I'll continue. Okay. This is a very professional operation, this YouTube channel. Super professional. So, alginate beads. We have the immobilized lactase enzyme. Lactase is the enzyme that converts lactose, which is the combination of the monosaccharides galactose and glucose, into their component monosaccharides. The disaccharide lactose is galactose and glucose. You separate them using lactase. People who are lactose intolerant, or lactase non-persistent, as is the proper term, have a genetic lack of lactose. They do not have, they have a genetic lack of lactase, excuse me. They do not have lactase enzyme. So, we have lactase immobilized in these beads. We pour milk that contains lactose through these beads. As it passes through these beads, we will get lactose-free milk. We will have galactose and glucose separated as it pours past. And maybe a little bit of alginate, but whatever, you know, it adds the flavor. It makes it a little thicker. It's nice. No, it doesn't. It's fine. All right. Now, here we have glucose test strips, P strips. So these are test strips, urine test strips. You take these strips and you take the pee sample, a cup of pee that your doctor has asked you to pee into this cup. Then you take the stick, and somebody, usually an unfortunate soul, probably a med student, is going to do this. Dip. Remove. It's called the dipstick test, the urine dipstick. Because you're dipping a stick into urine. Surprise. So this will cause enzymes that are immobilized in the foam that are these little squares right here. And that foam, each of these is a separate test. Each of these, 1, 2, 3, 4, 5, 6, each of those is a separate test. And those compare to color-coordinated charts over here, which tells you what your level of glucose in the urine is. Ideally, it's 0. You should have no glucose in your urine. If you have any glucose in the urine, you probably have diabetes, or pre-diabetes, or something along those lines. You should probably work that thing out with your doctor. You've got some problems. Now, glucose is, the entire point of this is you have immobilized glucose oxidase, which converts glucose and oxygen from the atmosphere into D-glucono-delta-lactone and hydrogen peroxide. The D-glucono-delta-lactone is going to be useless by this point, but the hydrogen peroxide is going to interact with the peroxidase enzyme, but is also bound to this pad right here. The peroxidase enzyme is going to be H2O2 plus a chromogen, which is a color indicator. The more peroxidase enzyme interacts with H2O2, the more chromogen is activated and undergoes a redox reaction, and the more color change occurs. The darker this dipstick test will go, and you have different levels of glucose in your urine. So that's the end of unit